Hi everyone. In this section we're going to take the implicit differentiation stuff that we've just learned and we're going to apply it to some more word problems. There were a couple of word problems in the implicit differentiation section, but these ones will be a little bit different. So this first one, I've already given you a formula. Let me rewrite it because it looks sort of funny up there. Q of p equals p squared plus 3p plus 1,200. And this function is outputting the units of a harmful pollutant in the air when population is p thousands. This, just so that I don't forget, is in thousands. Okay, so we know that the population is currently 30,000 and is increasing at a rate of 2,000 per year, and we want to know at what rate the level of air pollution is increasing. Okay, so we've been given this 30,000, and that is giving us a p-value. So this is like side note, known things. We know, remember p was in thousands, that when p equals 30, the population is increasing by 2,000 per year. Remember again, it's p is already in thousands, so I'm going to make that 2 per year. And I want to talk about what we're going to name this thing, because the naming is sometimes the most important. So this is telling us a rate of change of p. So this is a derivative of p. And this is with respect to a variable that actually doesn't show up here at all. It's with respect to time in years. So the units should help spot this a lot, but this is going to be what's new with related rates problems, is there's some underlying hidden third variable. Both things are changing with respect to time here, the population and the pollution level. And it's generally always time, so that's what you'll be looking for, things changing with respect to time. If we look at the question, we want to know at what rate is the level of air pollution increasing. So that is asking me to find the rate of change of Q. Once again, we need to think about this. How fast is it increasing? It doesn't actually say it very explicitly there, but that should be sort of implying to you, if you want to know how fast something is increasing, it's usually with respect to time, unless somebody really clearly specifies otherwise. So if it said with respect to population, then that might change the story. But here, I've been given a p-value and a dp dt value, and I'm looking for a dq dt. So this is always one of my first steps. If I need to, I write a picture to try and help me set up an equation, but here I was given the equation. So I'm just going to pick out all of the information and carefully give it names. Once you've got that, your equation and all your information named, what you want to do is take derivatives of this formula so that you get a new formula that relates not just Q and P, but dQ dt and dP dt. So we want to take the derivative of both sides with respect to t. So over here, we're going to get a dq dt, and you can keep the function notation if you want to, but I'm not going to since we're working on a third variable t. And then the derivative of 2p with respect to t, that means we're thinking of p as a p of t, right? So the derivative of function squared is 2 times our function multiplied by, oops, see if I can get it right, the derivative of our function, dp dt. Same thing here, remember that p is not our variable, so the derivative of our function is just the derivative of our function. And then the 12,000 is just going to drop out when we take the derivative. So this ends up being our formula. So we start with a formula that relates Q and P, and using derivatives, we can turn that into a formula that relates how fast Q is changing with how fast P is changing. So that's what we wanted. And once we've gotten this rate of change relationship, we can go ahead and start plugging things in. You want to be really careful not to plug in p equals 30 before you take the derivative, because as soon as you fix the p-value, you've made this thing constant. There's no change happening. We've already fixed the time and fixed the population, and that will fix the pollution. So all rate of change just becomes 0. So make sure derivatives before you start plugging in things that are changing. Okay, so if I go, I'm looking for dq dt, so this is really conveniently solved for that already. If I go through this, I have p equals 30, so I have 2 times 30, I have 60. dp dt equals 2, being really careful with units in this problem. 3 dp dt, so that gives me 6. So it looks like I'm getting dq dt is equal to 126. And then you want to make sure you always give units in these answers. So that's going to be units of pollutant per year. And again, you should just be able to spot it if this is the derivative of Q with respect to T. Q is units of pollution and T is time in years. All right, thanks for watching.